Continuing with section 4.2, now we are going to look at linear independence of two functions, because remember in the previous video I mentioned that the solutions, we want them to be linearly independent functions. So what do we mean by linear independence, and when can we say two functions are linearly independent? Two functions y1 and y2 are said to be linearly independent on the interval I if and only if neither of them is a constant multiple of the other on all of I. We say y1 and y2 are linearly dependent on I if one of them is a constant multiple of the other on all of I. So here is an example where we have to determine if the given functions are linearly independent or dependent. So we are given two functions. One is both of them are exponential. One is e to the 3t and the other is e to the negative 4t. So how do we show or confirm linear independence or linear dependence? We say, okay, let us say they are not linearly independent, so it means they are linearly dependent, which means one of them must be the constant multiple of the other. But before we do that, we also, because it mentions the interval, so we have to make sure that this interval is in the domain of the function. So now domain of e to the t and e to the negative 4t is minus infinity to infinity, all real numbers, and 0, 1 is in that, so we are okay. So now we assume that y1 is equal to, let us say that y1 is equal to c times y2, which means e to the 3t will be equal to c times e to the minus 4t, and which means e to the 7t is equal to c, because you can divide by e to the 4t on both sides and you'll get e to the 7t. But this is not correct on this interval, right? Well, throughout the whole domain of the exponential function, this is not correct, because exponential function is monotone. It's either an increasing or decreasing. So this one is increasing function and this is decreasing. But e to the 7t will be an increasing function and c is a constant. So an increasing function cannot be the same as constant function on the whole interval. Therefore, we say that we are getting at our assumption is wrong. So y1 and y2 are linearly independent functions. So this is called proof by contradiction. Another example, if we have t square cosine of ln of t and y2 is t square sine of ln of t. So again, we first check the domain of t square, cosine and sine, all three of them. The domain is all real numbers, negative infinity to infinity, and the domain of ln t, the logarithm function, is 0 to infinity, not including 0. And 0, 1 lies in each. So 0, 1 lies in 0, infinity and minus infinity, infinity. Now we again assume the contradiction. We assume that y1 and y2 are linearly dependent. So y1 is a constant multiple of y2. So we can write the function and we get this result. Now we want to divide the quantity on the right, leaving the c alone. So we divide by t square cosine of ln t. Right side becomes c, the left side gives us this conclusion. So now we can say, actually I think I did the opposite. I did y2 is equal to c times y1. Anyhow, so we get that, but that is tangent of ln of t is equal to constant. But again, tangent function is not a constant function, so we are getting at a contradiction, hence they are linearly independent. Now this next example, this equation is actually, if you notice, this is a third order linear equation, linear DE okay, with constant coefficients, and it's a homogeneous equation, okay, but it's a third order. So what will the characteristic equation be? Just remember in the previous case, so you just replace your derivative by r to the order of the derivative. So the third order, so we get r cube for it. Second order derivative, we get r square. First order derivative, we get r. No derivative, just a function, we get just 1. So our characteristic or the auxiliary equation will be this. Now this is a cubic function, so we don't have a formula for cubic function like we have for quadratic equation. So this is a cubic equation, so now we have to try basically kind of a guesswork. So we have to try a root, have to find one solution for this by check and guess and check method. So we start by plugging in r is equal to 1. When I plug in r is equal to 1, the left side is not 0. It is coming out to be 16, which is not 0. So we discard r is equal to 1. Now we check r is equal to negative 1. And by chance, this is giving us a 0. So we are good. So we say r plus 1 is a factor of the polynomial. So we will now divide the polynomial by r plus 1. So you can use either the long division or the synthetic division. So if you know synthetic division, you may use it, but I am going to show you the long division here. So now if you have forgotten, please review the long division stuff and be able to do it. So here on the left side, I have done the long division, and my polynomial coming out to be is r square minus 8r plus 25. So which means our characteristic equation or the auxiliary equation that we have had, it can be now factored as r plus 1 times r square minus 8r plus 15. Now this is a quadratic factor, so I can easily factor it, and if I cannot factor, I can use the quadratic formula to solve it. But this can be easily factored as r minus 3 and r minus 5. So we have 3 roots, which is correct. We should have 3 roots because it's a cubic equation. So the number of roots are equal to, and if we combine the complex and real root, they must be equal to the degree of the polynomial. So we get r is equal to negative 1, or r is equal to 3, or r is equal to 5. So now we will write our solution, because now we have 3 solutions, 3 values of r, so that we are now going to use 3 the linear combination will require 3 of the unknowns, and those unknowns are c1, c2, c3. So I write my solution like this. Okay, so this is the end of section 4.2. Now we will focus on 4.3.